Today we're going to study electromagnetic waves. The electromagnetic waves are made of two fields. The electric fields, which oscillate like this, for example. This is the electric field. It oscillates. I chose it to be oscillating vertically, so this is the electric field. And you also have another field that also oscillates, the magnetic field. So the magnetic field oscillates like this, horizontally. You see, I chose the electric field to oscillate vertically and the magnetic field to oscillate horizontally, but it can be the other way. But they're perpendicular 90 degrees, so they're vectors. Okay, they're like, let's see here, this magnitude of the electric field, this vector here, and remember this one is horizontal, the magnetic field here. There is 90 degrees angle between them. So the electric field is perpendicular to the magnetic field. So these electromagnetic waves is just two fields that oscillates, and they have a velocity, and that velocity or speed is the speed of light. So C is equal to 1 over square root of epsilon 0, and epsilon 0 times mu 0. Epsilon 0 times mu 0. This epsilon 0 and mu 0 are constants. So they're universal constants. So mu 0 is equal to 4 pi times 10 to minus 7. And for the units, you have Tesla, meter over ampere. And epsilon 0 is equal to 8.85 times 10 to minus 12. And the units are Coulomb squared over Newton and meter squared. Now, if you take these two constants and you plug them back here into this square root, and you do the multiplication and the division 1 over that, you get the speed of light, which is 3 times 10 to 8 meter per second. So this electric field and the magnetic field are related. They're related. How are they related? The electric field is equal to the speed of light times the magnetic field. That's how they're related. Now, these waves, they travel. They travel with this speed of light, these electromagnetic waves. They have a wavelength. So let's look at, for example, here is a wave. So the wavelength is you measure from this location to that location. So that's the wavelength, lambda. You can also measure from one peak here to one peak. This is also lambda. Lambda is the wavelength. So I put here wavelength. Now, this wavelength, okay, is equal to the velocity of the wave times the period. Okay, so the wave travels certain distance. So for it to complete a cycle means it starts here and then it goes around and then I come over here. That's a cycle. Okay, So that t is the period to complete one wave, like that. Start here, come down, and go up here. So that's the time for one wave. That's the time for to travel one wavelength. So this is the wavelength of the wave. Now this period here is related to the frequency in this fashion. The period is equal to 1 over the frequency. So we can change our equation to lambda is equal to V over F. And here is also another equation for the wavelength. Now, these waves, they have intensity, okay? The intensity of light. For example, if you put your hand in the sun, your hand gets warm because you have energy coming per unit area into your hand. Your hand, let's take for example the energy that goes all to your hand and divide by the area of your hand. That would be the intensity. Well, I said the energy. Instead of energy, I should have said the power. The power per unit time over the area. Let's see, for example, this is your hand. Okay, I just put here. Something like that. Okay, this is your hand. So this hand has certain area. The radiation will be coming in. Here's the radiation coming from the sun. So it's the sun sends electromagnetic radiation. So your hand is going to absorb some of the radiation that's coming from the sun. So you have certain intensity, okay, that your hand is taking. And that intensity is equal to the power that your hand receives, the power from the sun, over the area of your hand. Now the power is equal to the energy over time and over the area. So you can change the equation to this. The intensity is equal to the energy that your hand receives from the sun over the area of your hand times time. So this energy here is, we can change it to, this energy we can change it to the volume times the energy density. So this is, let's take for example the energy, because you get in two energies. Energies due to the electric field and energy due to the magnetic field. So if we say we're gonna try to find this intensity in terms of the energy due to the electric field. So this is the total energy, which is equal to the volume and times the energy density. So you take some, for example, some volume. Let's see some volume here in space. And this volume has certain energy. There is some energy there. So this total energy here is equal to the volume of that cube that you have times the energy density. And this energy, let me put here AT. I'm following this equation. Volume, energy density. This energy density, I make it U here, E, is equal to 1/2 epsilon 0. Remember the epsilon that we were talking about before? Times the electric field squared. So the intensity, let's take this energy density. This is the energy per unit volume. And when we plug it there, so I have the intensity, this is the intensity of the electric field, is equal to the volume, I put here the volume, and then I put here 1/2 epsilon 0 electric field squared over area times time. Now this V here, V is the volume. I can make it, let me change, I got out of the screen. So I'm gonna take this equation that I wrote here, this one here, I'm gonna put it here because we have room here. Let's put it here. We put it there. So we have the intensity is equal to the volume, and then I put here epsilon 0, the electric field squared, over 2, and this is the area, and this is the time. Now, this volume, we know if I come down here, intensity is equal volume, is area times the length. And here I put epsilon 0. The area times the length is the volume. I put here E squared, and I put here epsilon, 2. This is 2. And then I have A, and then I have T. A cancels out. But look at here, I have L over T. The length over time is a velocity. We can choose here the speed of light. So I put C, epsilon 0, E squared over 2. So here is the intensity of light due to the electric field. Okay. Now, what we need to do next, I don't have enough room. So what I'm gonna do, I'm gonna go to this location here, go around, and then I go here to this room here. I have space here. So if you look at here, you can see a part. This is the intensity. This is the speed of light. This is the epsilon 0, permittivity of free space. This is the electric field squared over 2. Now I show you here that the electric field is equal to CB. So what I'm gonna do here, I'm gonna put I, okay, and I put C, epsilon 0, I put here 2, and then I put the electric field. And you remember I have CB here, so I put C, and then B. Now you see I have the electric field, and I have this C and B. So this can give me C squared, the electric field, B, and then I have epsilon 0 over 2. This is the intensity. So you can have this intensity of light written in terms of the electric field and the magnetic field, the speed of light, and this epsilon 0. Now, if you look at here, you see this? We have C is equal to 1 over square root of mu 0 epsilon 0. If I square C, I get C squared is equal to 1 over mu 0 epsilon 0. So you see this is squared is equal to 1 over mu 0 epsilon 0. I have an epsilon 0 here. So this epsilon 0 can cancel that epsilon, and then I have only mu 0 there. I no longer have that C squared. So I go like this. The intensity is equal. I put here E, I put B, and here I put 2, and then I put mu 0. Okay? And that will be the intensity of light. Okay, so this is the final equation for the intensity of light in terms of the electric field and the magnetic field and this permeability of free space, which is this one here. So light has energy, okay? Light has energy, and this energy, okay, from this energy we can get the intensity, okay? So you have the intensity of light. So how much power you get in per unit area in some location. For example, the earth has an area facing the sun. So the sun sends the energy, okay? Sends the energy. Now, that energy is coming per unit time, so we have power. So every second we're getting certain amount of energy from the sun. So that's energy per unit time, we can call it the power. So if we take that power, which is the energy from the sun per unit time, and that power, and we divide it by the area of Earth, that's the intensity that the Earth gets from the sun. How much intensity? A sun intensity coming to Earth. So you take the energy that comes from the sun per unit time divided by the area of Earth. So this wave here, the electromagnetic wave, they travel with the speed of light. So they don't need a medium to travel. Okay? It's not like sound waves. Sound waves, they need air to travel. If there is no air, which means we have a vacuum, there will be no sound. You can't hear somebody speak if there is a vacuum, if that person is in a vacuum. But if that person is a vacuum and turn on the flashlight, you'll get the light. So the light doesn't need a medium to travel. It can travel in a vacuum.